Okay, so I think that now we have the concept that are necessary to analyze the design of an ultrasonic transducer. I have written here not only for NDT, but I would say that these are general concepts. Okay. So this talk, we will talk about ultrasound imaging, the role of the probes. We will talk about single element transducers, the characteristic of a transducer we have already talked about. We will go more deeply into detail in diffraction approach, and we will use some acoustic results to analyze the diffraction pattern of transducers. Of course, in NDT, but also in medical imaging, multi-element probes are very popular. And so we will discuss about the characteristic of multi-element probes. And we will see how we can make an electroacoustic characterization of this transducer. And finally, it will be time to conclude. So just to remind this figure that we have seen yesterday, when you have a region of interest that you want to image, typically you will have an impedance mismatch between various regions. And at each impedance mismatch, you will have a reflection coefficient, which means that you will have a reflected wave at each impedance mismatch that will generate various echoes. So this representation of the amplitude versus the time is typically what we call a scan. But if now we decide to move the transducer from one side to another, then we will be able to reconstruct the region of interest. And this is how we make imaging. Of course, you have the possibility to move mechanically one transducer, but very often you are using multiple transducers. And these transducers are, for instance, array transducers that can be used for NDT. They are all flat transducers, but here, for instance, you have transducer for medicine. And here you have curved array transducer, linear transducer, and various step phased array transducer, and so on. What is the role of a transducer? First, the role of the transducer is to make the electromechanical transduction. So this is one of the main functions. This is to convert the electric signal that you have sent into the probe to a mechanical signal, and conversely, to convert the mechanical signal, because you are working in a pulse echo mode, to an electrical signal. So the electrical wave is transformed into an acoustic wave, and vice versa. This is the first role of the transducer, doing the transduction. But there is also a second role. This is the beamforming. And the beamforming is done by focusing. And you have two aspects. First, you want to have resolution because you want to produce images. It could be simple images or even quantitative images. So you have first the focusing. This focusing, of course, can be achieved by shaping the piezoelectric transducers into a focused transducers, or by using a lens. It is also possible on the front face. But also, if you have an array transducer, which is a juxtaposition of many single element transducer, you can do a beam scanning, which means that you will, on your transducer, solicited only a few numbers of transducer, let's say, for instance, 8 or 16 transducer over 128, and you will move this synthetic transducer along the array to produce the image. So the beam scanning is the second point. To obtain an image, the beam direction must be changed, and it can be done, of course, mechanically if you have got one transducer, or you can use electronic if you are using array transducer by switching specific transducer on or off, or by using electronic delay. So this is the role of a transducer when we want to do some image. But no, if we are looking, I've already talked about that, in a transducer, the heart of the transducer, this is the piezoelectric material. So what are the characteristics that are very important for transduction phenomenon analysis? First, this is the coupling coefficient. And as I said, it is defined for each vibration mode. The coupling coefficient, higher, it is an indication of the energy conversion. And of course, you will have to tend to get the highest coupling coefficient into the material. It is a criteria, absolute criteria. If you are able to transfer the most energy you are able to transfer, better will be your images, or you can lose low energy, and etc., etc. The second criteria that you have to consider, because you have transmission reflection and multiple transmission reflection, this is the acoustic impedance. Typically, in a ceramic material, the acoustic impedance is around 33 megarelays. When you want to propagate in water, the acoustic impedance of water is 1.5. So you can see that you have an impedance mismatch. So the question is, how can I manage the impedance mismatch? If you want to propagate, for instance, in steel, the steel has an impedance of 45 megarelay. So here again, you have an impedance mismatch. It is less, but you have the impedance mismatch. So how do you manage that? So the acoustical impedance is a very important criteria for ceramics. That is the heart of the transducer. And finally, there is also an electric criteria, which is the dielectric constant. The dielectric constant, you know, as I said before, ceramic material are dielectrics. So they are insulators. If they are insulators, it means that the epsilon, or the capacitance of this insulator will depend on epsilon and will depend on the geometry of your transducer. If you have a small transducer or a small capacitor or a large capacitor. Well, so it means that this will affect very often, not very often, this will affect the matching to the electrical environment. And this electrical environment is very often 50 ohms. And then we can see that all these parameters, especially the dielectric constant and the coupling coefficient, will have an importance on characteristic of the transducers that I will define later, but I can use the word right now. This is that the sensitivity of the transducer, this is the ability of the transducer to detect very small objects, for instance, this is very sensitive. And the bandwidth of the transducer, this is the pulse duration, more or less, which will give information on the axial resolution. And so what you have to remind, this is that the epsilon, the electric impedance, input electric impedance of a transducer is proportional to the inverse of the dielectric constant. Just to make a short digression on a specific class of material that is used now very often in transducers, these are piezocomposites. So piezocomposites, you understand that, for instance, if you want to work or operate in water, the piezo composites are very interesting because, as I said, water has an impedance of 1.5 megarelays, and ceramics has an impedance of 33 megarelays, 35 megarelays. So very strong impedance mismatch. Now, if you mix a polymer and a ceramics, you will lower this impedance. And composites, you can make composites of various connectivities. So for instance, you can define the connectivities between two, if you consider a two-phase material, you can define the connectivities as follow, with 4 values. First, if you have, let's say, for instance, a complete connectivity, like air in this area. So it means that in the 3 directions, you are continuous. But of course, if we look at each individual person that are in this area, they are not connected together, which means that they have 0 connectivity. So I would say that, for instance, if I look the people that are in this theater and I want to look at the connectivity is 0, 3. 3 for air, 0 for the people that are there. So you can decline the various connectivity of the material from 0 to 3, having 4 values. 1, you have connectivity in 1 direction. 2, you have connectivity in 2 directions. And 3, you have connectivity in 3 directions. And so there are 2 connectivities that are of particular interest. This is a 2-2 connectivity, a polymer matrix with ceramic plates, like this. And you have the 1-3 connectivity. This is ceramic rods in polymer matrix. Donc 3 connectivity, 3 for the polymer and 1 for the ceramics. And if you look at the 3-3 connectivity or 1-3 connectivity, this is ceramic rods in polymer. And you can do this type of material. This is very interesting because the material is, as it is polymer based, it is conformable. So you can shape the material to lengths, for instance, to make lengths, or to make curved array. And here, just to explain the technique, you start from raw ceramic, and then you dice. This is a dice and fill technique. I dice the ceramic. So here I have a 2-2 composite. And then I dice in the perpendicular direction, and then I fill with polymer. And then I remove the bottom of my ceramic. And then I get my 1-3 composite. So this is a dice and fill technique. And what is interesting here, this is that if you look at the properties of the material, these composites, you can see that even that if you look at the volume fraction, the impedance varies between that of the resin and that of the ceramics. And typically for a resin, it is 4 megarelays. And for a ceramic, it is 33 megarelays. So you can make materials with 12 megarelays without any problem. And the epsilon is a compromise between that of the ceramic and that of the resins. So it depends on, typically a resin has a dielectric constant around 2 or 3, while ceramics can have a dielectric constant around 2000, for instance. So you simply divide by 2 your electrical, your dielectric constant when you have 50% of ceramics. And the coupling factor, I will not go into detail, but what is that have been surprising at the beginning, this is that even the coupling factor of 1-3 composites is higher than the coupling factor of a plain ceramics. The thickness coupling factor of a plain ceramic is lower than that of a 1-3 composite. And this is essentially because you do not look at the same vibration modes. In one way, if I go back to this transparency, you have the coupling factor, the thickness coupling factor of the plain ceramic that is here. And here you look at the thickness coupling factor of a ceramic rod. and it is not the same value because it is not the same vibration modes. And this one is higher than this one. So just to say that in terms of technology, when transducers are used, especially for underwater immersion transducer in water, not necessarily in NDT and contact transducers, but sometimes they are using also composites for array transducer in NDT, because even there is one of the main advantage. This is that to say, okay, if I want to make multiple element transducer, okay, if I am clever, I just make a wall composite and I put electrode where I want, and I can make array transducer. It's quite nice. I do undercut to avoid coupling between elements, but I can make very rapidly multiple array transducers by just laying down electrodes. It is quite nice. Okay, so just to say that this is today the material that is used. Now let's go back, because before talking about multi-element transducer, let's talk about single-element transducer. So here, for instance, you have a picture of immersion transducer that we can use at the laboratory with various diameters, various size, various frequencies. How is made a transducer? Typically, you have the piezoelectric element. It could be a composite or not. And this piezoelectric element is electroded on both faces, and you will attack and receive through this piezoelectric element. But this piezoelectric element is not alone. On front face, I have discussed the problem of the impedance mismatch that you can have when you want to propagate. So you will put matching layers. These matching layers, they have the role to transfer the energy in the propagation medium. And on the rear face of the transducer, you have a backing material, because you have to remember that the wave, if you send an alternative pulse at the resonant frequency of your materials, you will send a wave on the front face, but we will send also a wave on the rear face. And if you don't put any material on the rear face, okay, so it means that because of the reflection coefficient close to 1, nearly most of the energy will be transmitted into the front face, and we will discuss what will be the consequence of that. But if you use a material, the wave that is here, you will want to attenuate these waves, because you don't want to have a round trip echo that comes from the rear face in this backing material. But not only want to attenuate this phase, but in fact, because you put an acoustic impedance on the rear face, you will damp the vibration. And we will see what is the effect of this damping. So the center frequency of, let's say, the resonant frequency of the transducer is more or less given by that of the ceramic. Of course, because you have embedded your ceramic into several materials, it's not exactly the resonance of the ceramic, but it is close. So in the first approximation, we will say that it is close to that of the ceramic. And it is given, the calculation, I will not explain again the resonance mode, but just to say that typically for 1 millimeter thick ceramic, we have a 2 megahertz resonance. Okay. So now we will discuss the role of the transmission reflection coefficient by applying the formula that we have done, we have seen just the lecture before. We already did this calculation, if we want to calculate the transmission coefficient of a wave from a ceramic, an ultrasonic wave that goes from the ceramic to the air. First question. In fact, because of the, remember, the air, the acoustic impedance is 44 relays. The ceramic, this is 33 mega relays. So you have 10 power 6 or 10 power 5 difference between the two materials, which means that all the energy in air, when you have air on the transducer, is reflected. So imagine that you have a ceramic with air on both faces. You have a pure resonator. And when you send a wave at the resonant frequency, the wave is trapped into this resonator. And of course, the wave attenuates because of losses into the material, mechanical losses and the electric losses. This is why when we are using quartz as a resonator, quartz has a very low mechanical and electric losses, which means that when you do a resonator in air with such quartz material, you have a very, very long oscillation, and it can be used for clocking. But now, look at the same calculation. If now you want to transmit into water, into water, the acoustic impedance is 1.5 megarelays. And if you do the calculation, only the reflection coefficient is 0.9, which means that less than 10% of the energy is transferred into the material, in the propagation medium. Less than 10%. Okay. So now imagine the following situation. On one side, you have air, and on the other side, you have water. So it means that, in fact, the energy on the rear face will be, when you have a vibration, the energy will be completely reflected and will be transmitted in the front face. So you have a, that is just to understand that. So it means that at each round trip into the ceramic, or the piezo material, you will have only 10% of the energy that will be transmitted into water. So at the first round trip, you have 90% of the energy that remains into the ceramic. At the second round trip, you have 19% power 2 that remain into the ceramics. At the third round trip, you have 19% power 3 that remain in the ceramic, till it tends to 0. Which means that, in fact, what you will get at the end into water, this is a very, very, very long pulse, having several tens of periods. And if you want to do images, this is not what you want. Because if you have two structures that are very close together, and you have a very long pulse, you will not be able to separate these two structures. So the question that we address, this is how can we shorten this pulse? Just to get a pulse duration of 1 to 3 periods. To do so, you have two solutions, two options that you will use. Improve the transmission from the ceramic to water, for instance, or to the propagation material, or second option, absorb the energy that is emitted on the rear face of the transducer. So, first wavelength, some equations. It is based on interference principles. We will use what we say matching layers. Okay, what is a matching layers? In fact, if you interleave a layer between ceramic and water, what you want, this is to get a destructive interference between the wave that have been emitted first and the wave that have been emitted and that was reflected through this layer. So if you want to have this opposite phase, what does it mean? It means that in terms of spatial consideration, having two harmonic waves that are in opposite phase, this is to say that they are just shifted of half a wavelength. So it means that the round trip that you have here, 2 times the thickness of your layer, has to be equal to half a wavelength. And this, in this case, you will have an opposite opposite phase. And if lambda over 2 is equal to 2 times the thickness, it means that the thickness of your layer should be lambda over 4. So this is what we call a quarter wavelength layer. Simply, the calculation is very easy to understand based on interference principle. This is a quarter wavelength layer. This is why we are talking about that. This is the same principle that we have on our glasses, when we have a non-reflective coating on our glasses. We are using quarter wavelength layers, of course. This is the same principle. So this is first the thickness that we have. But no, the question is, okay, we have an impedance ZC on one side and ZE on the other side. How do I select the intermediate impedance? It is a little bit more complicated, but maybe you remember, for those who have done some chemistry, some mechanics or some electronics, transmission lines, but we can express the impedance seen in x equal to 0 through this layer. And the impedance is given by this expression. Okay. Because the thickness is equal to lambda over 4, it can simplify very easily, and we get the following formula. The impedance is given at x equal to 0 to dl, which is the impedance of the layer, square, divided by ZE. Okay. What do we want? We want to have an optimal value, and we want that the effective impedance of the ceramic in x equal to 0 equal to that of the ceramic. So we can write the following formula as ZC equals ZL square divided by ZE. And so we can deduce the acoustic impedance of the matching layer as being the square root of the product ZE, ZC. It's very simple. Okay, but if you look at the formulas, and especially this formula, K is a wave vector, it is 2 pi divided by lambda, and so it is related to the frequency. So it is given for only one wavelength or one given frequency. And of course, when we have a pulse that has a duration of 1 to 3 periods, for instance, it is clear that the bandwidth of the transducer is not only one period, one single frequency. You have a bandwidth. So it is not really an optimum. And there were a compromise that was found by several authors in 80s, and that says, okay, instead of using this formula for broadband transducer, which is the case of the transducers that are generally used, the optimum impedance value is given by this formula. Instead of taking the square root, we take the cubic roots of the product ZC multiplied by ZE square. Okay. So this is the two characteristics of the matching layer, quarter wavelength layer, and acoustical impedance. Now, first rule, try to enhance the transmission of a wave into the propagation media. And we will see what result it has on the electroacoustic response of a transducer. Now, let us look at the backing material. The backing material, it has to absorb and disperse the energy from the rear face of the ceramic. So how do yesterday I explained how to create an acoustic, how to create an impedance matching like this. Now, I will explain what is the role of the backing to try to reduce the time duration. So, of course, it has to absorb the energy. So let's say, for instance, you have a polymer matrix and you have a grain or a metal polymer composite that is used as a backing material. And metallic particle will be diffuse particles, and then energy will be lost. So you have this aspect. But the damping is very important. And how can you imagine the damping? So just say the following analogy. The ceramic, it is like a cymbal. So if you hit the cymbal, then it will have a long durations. But you can reduce this duration by doing what? If you put your hand on the cymbal, you will rapidly reduce the time durations of the cymbal. And using the backing, this is more or less equivalent to put your hand on the cymbal, just to reduce the duration. So you can see that in this way, what will happen? When you put your hand, you absorb energy. And this is exactly what you do, and the role of the backing, absorb energy. You absorb energy and disperse the energy. But of course, the pulse duration will be shorter. But even by this simple analogy, you can say, okay, it is shorter, but it is also lower. Because we all know that if you put your hand on the cymbal, then the sound will be lower. And here again, the sound will be lower. So that's the role. So the backing has two roles: damp the vibrations and absorb this vibration on the rear face of the ceramic. Ideally, if we have a backing having the same value of the ceramic, all the energy that comes that rise on the rear face is absorbed, and we have a single an echo shape, perfect echo shape like this. Okay. In practice, I would say impedance is intermediate to that of the ceramic and the propagation medium, and to that of air. Typically between 1 and 10 megaRLs, but it can be higher. So what is the effect on the transducer? So now let us look. You have just a piezo, and I start from the original piezo. On one side I have air, and on the other side I have water. And you can see the long time response that you have. And so, which means that the poor axial resolution that we have already defined this parameter, and the narrow bandwidth of your transducer. Now, if I put, alors, also an important parameter that we can compare, this is to look at the impulse response. And the amplitude of the impulse response, this is 2, just forgot the 10 power, but just to say in relative amplitude, it is a little bit larger than 2. Now, if I put a backing on the rear face, so I have my backing here. And for instance, I have used a backing of 4 megarelais on one side and 10 megarelais on the other side. What you will see, this is that you reduce the pulse duration. But you reduce the pulse duration, but look at the amplitude. No, it is less than 2 for 4 megarelais and much less than 1 for 10 megarelais. So you have absorbed energy, and so you absorb energy. So it means, what does it mean? It means that the sensitivity of the transducer is lower. So you have done this damping. So have you reduced the pulse echo response? And now, if we put a matching layer, so here we have the comparison with 4 megarelais backing, if I remember. Yes, 4 megarelais backing without matching layer and with a matching layer. You have, again, an improvement of the transfer of energy and a reduction of the pulse duration. And this is very interesting because here, again, now look at the amplitude of your signal. The amplitude of a signal is improved, and you have win on the sensitivity because you have catch some energy that should go in the backing, you have catch it to put it in the front face. So you do improve both the bandwidth of your transducer and the sensitivity of the transducer. This is one of the major effects of the matching layer. So in conclusion, quater wavelengths matching layer allows to increase the sensitivity of the transducer and increase the bandwidth of the transducer, while the backing increases the bandwidth of your transducer, but reduces the sensitivity. The higher the acoustic impedance of the backing is, the less in the sensitivity. The best signal that we can obtain is having a signal that has only one period, but it has a poor sensitivity. And in terms of medical application, for instance, this is not what we need. We want, it could be managed for NDT, because I think that if you take a metallic piece, whatever the amount of energy you put in it, you will not damage it unless you really send a huge energy. When you are designing transducer for medical applications, of course, you have to be careful about the amount of energy you can put to your transducer, because it can become dangerous if you have some artifact that appear in the manufacturing. So we don't necessarily want to have a poor sensitivity in our transducer, because poor sensitivity means that you have to put more energy in the body to make images. So just to precise what we call the sensitivity and the characteristic of a parameter of a transducer, if you take a transducer and you have a target, a small target, then you will make an echo on the target, and the amplitude of this echo will give you the sensitivity. Higher is the sensitivity, of course. Smaller structure, you will be able to observe. It's quite obvious. And so it means that with very sensitive transducer, you are able to look far away, very far. So that's one point. And for instance, if you are doing inspection in metals, having sensitive transducer is very interesting if you have big pieces, because you will be able to observe defects at a very large penetration depth. That's the idea. And so how do you measure this? So it's not very complicated. You have a generator, a pulse generator, and then you have a target, and you measure the pulse echo sensitivity as being the ratio of the received amplitude at a given frequency according the excitation voltage. And this ratio gives you a value of sensitivity at a given frequency. Let's go back to the definition of the axial resolution. Because yesterday I was fast, I was rapid. If now you consider two targets that are close together, if you have a highly sensitive transducer, very often you will have long signal, because in a way you have a compromise between the sensitivity of the bandwidth of the transducer. Just for people that are from electronics, this is the gain band compromise that you can have in operational amplifier, for instance. But the idea is to say, okay, let's say I have 1 watt of intensity that I want to put in my body. This 1 watt, I can put them in various manner. The first manner I can say, this is, okay, I will be very narrow band, but very high peak. So if I am narrow band, I have a long pulse duration. But the other option I can do, this is to say, okay, I'm broadband, but I have low amplitude. And the energy which is given by the area of your curve will be constant, but it will be distributed differently. So if you have, very often when you have a large bandwidth, you have low sensitivity. And when you have narrow bandwidth, you have high sensitivity. So here, and high sensitivity means long pulse duration. If you have a long pulse duration, what does it mean? Here, in fact, you have a long pulse duration. You will not be able to discriminate two targets that are close together because of the long pulse duration. But if you have a short pulse duration, you will be able to separate these two echoes. And so you have a compromise that you do between the sensitivity of a transducer and the axial resolution you want into your transducer. And the axial resolution is as follows, is defined as follows. So here you can separate the two targets, but not by taking the envelope. But if these two targets become closer, there will be one time where it will not be possible to separate the two targets because you will have only the envelope of one echo. And the time that's to separate the two echoes is given by delta t equal to 2 times the distance between the two targets, because you have a round trip, divided by the celerity. And so the axial resolution is given by d multiplied by c over 2 multiplied by delta t. And that's it. The echo duration is determined from the half duration of the envelope. It is inversely proportional to the bandwidth, if we assume a Gaussian shape. So here again, the method to measure, you do the measurement in a water tank, you send a pulse, and you measure the envelope by various techniques, but you have a signal processing technique that allows you to measure this envelope. It's not complicated. So that was the point I was discussed. Remember the property of the Fourier transform. The pulse duration will be directly related to the bandwidth of the transducer in the Fourier domain. So long pulse duration narrow bandwidth and short pulse duration broadband transducer. Having a high resolution transducer is equivalent to say that we have a large bandwidth. Now, again, I will talk about the lateral resolution. This is more or less the same discussion that we had yesterday, but you can, and we have right now. This is the ability of a transducer to separate two targets, but in a transverse direction of the propagation path. And here you can see that you have clearly the separation of your two targets, and a good resolution is given by a narrow beam. It is clear that a flat transducer has a very poor resolution. And of course, to measure the radiation pattern of a transducer, and this is always the same basic principle, except that here you have a target, what we call an acoustic hydrophone, that will measure the pressure locally, and you will make a cartography of the field generated by your transducer. What you will look after, this is first the lateral resolution, which will be given by the minus 6 dB width of your transverse field. And the other aspect is along the axis, you will look after the focus point, of course, and the depth of field, which is the half bandwidth, again, in terms of spatial distance, where you have good resolution. So the depth of field for people that are doing photography, this is exactly the same principle. This is the region where you will have good images, or where it is well focused. To detect small structure, it is clear that we need to have sensitivity. To differential two nearby structures, we need to have resolutions. That's it. So let us give some typical values that we have in transducer. In transducer, we have typically -4 to -12 dB sensitivity. The axial resolution is from 1 to 3 wavelengths. It means that, for instance, at 3.5 megahertz, the axial resolution, if we say that it's 2 wavelengths, then it's 0.5 millimeters. And the lateral resolution typically is from 2 to 5 wavelengths at the focal point. Here again, just to have a correct representation of images, I had discussed this point yesterday, it is nice to have lateral resolution and axial resolution that are close together, in order that the images that you produce of a cycle is a cycle and not an ellipsoid, for instance. Okay. Of course, you have to think about the fact that when you are using transducer, and especially focused transducer, the lateral resolution is degrading when moving away from the focal point. Okay. Okay. I'm just checking. I have. How long do I have? 40 minutes. Something like that. 40 minutes. I don't know. Yeah, maybe it will be okay. I don't know. Just talk about the diffraction approach, because it is an important point. Just to understand diffraction, why do you have an enlargement of your beam due to diffraction? Of course, we can go back to diffraction theory and apply the Huygens principles and say, okay, and so on and so on. But this can be explained in a very simple manner by just considering the interference of two waves. if you say, okay, let's say, for instance, you have a transducer, and you have a wave on this transducer that is emitted at the center of the transducer. And let's say that you have a transducer, a point on the edge of the transducer, and you have a wave emitted on the edge of the transducer. Then, of course, if you are located in a transverse direction, here, for instance, there will be a distance where the interference of the wave emitted at the center and the wave emitted on the edge will be destructive. Mean that you have an opposite phase, because the March difference, delta, here, will be equal to lambda over 2. And then what does it mean? It means that you will get a zero amplitude or zero intensity locally. So this is why you have an enlargement of your beam here, simply by considering this interference of these two waves. So the way the March difference lambda over 2 is given by the diameter of the transducer divided by 2, the radius, multiplied by the sine of the angle. And if this sine is small, the angle is given by lambda over phi. Maybe 2 is missing. No, lambda over phi. That's it. So this is this explains the spreading of your field. Of course, it is more complicated, but this is a simple way to explain the diffraction. As I say, in fact, you have a beam spreading into the material, into the medium, which means that if you have a region which is named the Fresnel zone area, where you have multiple interferences, and then at one time it becomes smooth. And as it becomes smooth, you enter the Fraunhofer region. And there is a limit that is given by the diameter divided by 4 times the wavelength that separate the Fresnel zone from the Fraunhofer zone. And the divergence of the field is proportional to the number of wavelengths contained in the transducer and the impeller. That's it. So this region is called the far field region. And in the far field region, of course, the larger the transducer, the narrower the beam, and the smaller is the transducer wider, the wider the beam. Okay, so this is for plane transducer, but of course, plane transducer have a poor lateral resolution. So they are not used for imaging. So we are doing focusing. So to do focusing, you can do some mechanical focusing. And you want to focus at F axis. And so you can do some geometry and calculations. And you can do a parabolic approximation, because the difference here, delta, that you want to make a focusing, of course, it should be along a circle. But in the first approximation, it could be parabolic, and which means that you will neglect the term delta square in this equation. And so you can say that you have this relation, f squared plus y squared is equal to f squared plus 2 times f delta. And then you can have the path difference, delta, which is given by xy divided by 2f. And so this is how you do, simply by curving your transducer, you can do shaping of the transducer. But now, for instance, if you are using array transducer, you can manage the delay, and the delay should be given by the celerity into the material, into the propagation media, here water, and for instance, and it is given by delta over C2, or it could be in steel. If you want to focus in steel, it could be steel celerity, and so it is given by, so the time delay is given by this formula. If you create an advance is achieved by another material that you add in front of your transducer, then it doesn't have exactly the same property. So this one has a specific celerity C1, and while the medium has a celerity C2. And then you want to create an advance length such that the time advance is given by tau prime is given by this formula. And especially, again, by applying Pythagoras theorem and approximate the thickness to be to thin length, then you can write that this thickness should be y squared over 2r, where r is the radius of curvature of the lens. And then the time that you need to create for the advance is given by this formula. But remember that we want to have also a time focusing at this focusing point. So we want that this time equal to this time. And so this gives us the radius of curvature of our lens by this formula. So now let us look at some results. If you have non-focused transducer, the optimal region for each insertion is given here. And typically the beam spreading is given here. It's the diameter divided by 4. And low focusing, and high focusing, and narrow beam width. And here you have the acoustic focusing here that appear. Just to have here some formulas that give the depth of field and the acoustic focusing formulas and the lateral resolution in your systems, typically. So this is, of course, higher is your focusing, better is your resolution. Now, if I look to arrays, I said that it is a juxtaposition of multiple element transducer. So that's a transducer design where you have each element. Typically, you have 100 to 28 to 256 elements, and even you can have a higher number of elements. You have the piezo material, of course, very often a composite material. You have the matching layer, you have the acoustic lens, and you have the backing materials. And this could be linear or curved array. So you have to manage the delay again to make the focusing. For instance, here you choose to solicit 5 transducers to make focusing, and then you make the translation to make the imaging. So we are talking about beam forming here. And then you can calculate according the various characteristics of the focusing, the time delay that you should apply to electronic elements for focusing. Let's do an application, for instance. If you have a pitch of 1 millimeter and you want to focus at 60 millimeters with a celerity of 1500 meters per second, then the time delay unit would be 5.5 nanoseconds. Okay. Just a remark. just to say, let's say we are operating in 1 megahertz. 1 megahertz, that corresponds to 1 microsecond. So it means that images, and typically we want to propagate on few centimeters. So typical range of ultrasonic signal is comprised between, let's say, 0 and let's say 100 microseconds, maybe 1 millisecond maximum. And even if you propagate on 1 millisecond, it is quite long. You go quite far. To make images, the high sensitivities, it is 24 hertz. So you have time between 1 millisecond and 1/25 hertz, which means that it is 40 milliseconds. You have time to do things electronically. And especially what you can do, this is to do multiple focusing at various penetration depths to get, again, better resolution and to avoid the problem of depth of field. So during this time, during 100 microseconds and 40 milliseconds, you have plenty of time to do some several things. And so, of course, during so you can have various multiple shots, and during these multiple shots, you can vary the depth. Of course, this will slower your system, but now you can manage this. So you can make focusing at the emission, but as you are doing emission and reception, you can also modify the delay so that the receiving focusing will vary again. So you can make double focusing at the emission and the reception. And now processing is so fast that it is done in echographic system, both in industry and medical applications. So the problem is that you have multiple array, and it is, let's say, you have one problem. This is property of the Feuillard transform, but imagine that you have an aperture like this. In fact, the radiation pattern of your transducer or your array will be the product of the radiation pattern of one single aperture by the periodicity of the material of the array. So by doing so, you multiply two things: the aperture width. You do the convolution of the aperture width here by the periodicity of your aperture. So it means that you will create what we call lateral lobes. So you want to have this because you synthesize a very narrow band system, but because of the periodicity of your structure, you create side lobes. And of course, these side lobes are unwanted because you will image on the side, and that is not what you do. This is not at all what you want. So what you will do, this is try to reject this side lobe very far, not to see them. So, and this is what is written. We want to push them back to 90 degrees. Okay, how do we manage this? In fact, if you take an element that has a width of about lambda, its radiation pattern will be close to that of a point source. So it means on a point source, this is a circular radiation pattern. So, and this will be the rule that will be used to put this side lobe very far and close to 90 degrees. So here is a typical structure of an array probe. So you have the backing materials here. Let's say it's an element. So you use a composite material. Typically, here, this is a 2-2 composite material. Here, because you want to avoid the intercoupling element, you have in green a cut that is done to avoid propagation of wave in the transverse direction. You just want to have transverse in this direction, the vertical direction. And then you will have matching layer. Very often you have more than one matching layer, and the focusing. And you create a partial cut into this element to avoid multiple resonance in this element. Here is an example of a design. So let's say the width L of one element, we say it's 1.5 wavelengths into water. So it means that in water it's 0.5 millimeter. The thickness of the ceramic that we will choose for 3 megahertz will be half a wavelength. So the wavelength into the ceramic, so it will be 0.75 millimeters. So it means that you can see that the width is equal to the thickness, and this is not a good thing because this will create multiple vibration modes in multiple directions, and this is why we will cut the ceramic, and this is why we have this interspacing cut to avoid vibrations on multiple vibrations. And then you do a subdicing, typically between 2 to 3 into the element in order to get 3 elements. And this is why you have dicing here, to get 3 elements and to respect the separation of vibration modes. And then you have the ceramic, the rear electrode, and so on. And you will get 192 elements, and the 8th of the elements is 10 wavelengths, typically in water. So 7.5 millimeter. So here you have an example of phased array. So you are doing not only focusing, but you can manage deflections. So this is very useful in metals because you put your probes and then you can just look on the side to generate and to inspect weld, for instance. This is very useful. And for medical imaging, it is important for heart imaging because of the thoracic cage. You cannot access directly to the heart, so you have to enter by this under the costal, and then you have to use a phase array transducer. You can have some annular arrays also, more for medical applications, and various techniques for scanning. So I have already talked about that. And you have also multiple row array. This is a very strong tendency to say, okay, I have talked about linear arrays. But no, because of the technology, we can also, for instance, subdicing the transverse direction and do a focusing with these elements in this direction to improve the resolution again. And so you have a 1.5D arrays and 1.75 where you can manage also the delay on this direction. So this complexify, of course, your echograph and your transducer, but people are doing that. And the problem is that you want to increase the number of elements, but if you increase the number of elements, each element has to be connected. So let's say that you have 92 elements, and you multiply by 5 elements each star, it means that you have 1,000 elements that are connected, nearly 1,000 elements. And it means, how do you manage this? With big wires. So you have to find other issues to make the electrical interconnections. And now you can use MUX, multiplexers, to interconnect elements and use technology that comes from microelectronics to do so. But anyway, at the time, you may have a very big cable. It's yeah. So you can use matrix array also to do 3D imaging, of course. But here again, the difficulty is to improve, to manage the interconnection. What are the technical issues for matrix arrays? The number of elements, which is very high, controls the electronics, and having the various operating modes. So people are using either sparse array or fully connected arrays. And the separation of transmit or receiver elements, which allow sparse array for transmission, sparse array for reception, which limits the number of elements, and so on. And the volumes data, of course. And so you have also the question of the integration of the electronic into the probe using MEPS technologies. Okay. Just to say that we have seen some aspect on the transducer design, but of course, behind this, you have simulation tools. And in the first approach, you have electroacoustic models that are based on equivalent electrical circuits. And these one-dimensional models are very good models because they are simple, they are fast, and they can predict all the performances of a transducer. Sensitivity, bandwidth, axial resolutions, electrical impedance, and so on. If you use a diffraction principle, you can calculate the radiation pattern. And so you have all the characteristics of the transducers. For a single element, very often this is enough to analyze and to design a transducer, a single element transducer. But now if you are working with multiple element transducer, you can put this model in cascade, but there are several effects that you cannot take into account, such as the coupling of one element with the other. And so in this case, you can use much more complex models that are based on finite element codes. So you have Attila codes, you have piezoelectric, ANSYS, and so on. You have COMSOL that you can use also. And these models will allow us to determine all the characteristics of the transducer. Even including the consideration on the electrical environment, of course. Mm-hmm. And for instance, if we look at the transducer simulation models, the KLM model is very simple. It is a cascade model. And one of the main advantages of the KLM model, this is that if you look at ceramic, one thing I haven't said, this is an hexapole. Because you have an electrical port, and you have two mechanical ports. So you have done an hexapole. And one of the main advantages of the KLM model, this is, in a way, it transforms this hexapole into a quadrupole. Because what you will look in a preference way, this is what's going on from the electrical to the front face, and from the front face to the electrical. That is the difference, the major advantage of the KLM model. But all the models are equivalent, for, obviously. And then you will get the electroacoustic response. For instance, here you have the pulse echo response with simulation and experiment of 35 megahertz transducer. In terms of sensitivity also, you can see that it is quite nice. You can do also some modeling of the acoustic field using Huygens theorems. Just to have to remind that Huygens theorem stands that you can, any sources, you can use it as a sum of circular waves. You can decompose a finite source as a sum of circular waves. And so just to make this decomposition, you have to be careful to have at least a 10-point source per wavelength. And this will allow to determine the lateral resolution, the lobe noise level, and the depth of field, of course, with new system. Okay. So the technology and therefore the design of an ultrasonic probe is very complicated, you understand? It has to be optimized, the two essential functions, the transduction on one side, and the beam forming on the other side. It is therefore necessary to optimize the quality of the piezoelectric material. This is why you have research on piezoelectric materials, but on new transduction mechanisms, but also the configuration of the transducer in terms of damping, attenuation, to improve the compromise between the sensitivity and the bandwidth. I think that you have understand that you have to make this compromise, because high sensitivity means poor resolutions, and low sensitivity means high resolution. So you have to understand that. It is also necessary to optimize the geometry of multi-element sensors in order to ensure good beam formation, focusing plus scanning, in order to make 1D images or 2D, 3D images. And I think that's all for now. And we have time for questions. Thank you.